Recording. Okay. Now recording and I'm sharing the screen. Thank you. Be alert on that, okay? Because it will be a very difficult thing. I don't see in my screen if I'm recording or not. Okay, anyway, so okay, good. So let's go back here, okay? So we got A1, A2, and 3. And as you can see, these constants will be function of these values. These are the joint values, the nodal values, and also the positions of these joints. Okay, so we can replace this into the polynomial of interpolation here, A1, A2, and 3, and rearrange. Okay, so we get this replace in A1 plus A2x plus A3y and rearrange. So we want to write this, but in every term we get, okay, those terms which are multiplied by ui. And all of these we collect in one single term, which is n1, ni. So we said u, xy, we put it like this, n1, which depends on ny, n2, and n3. I didn't have space here. And these are multiplied by ui, uj, and uk. Okay? So the process is the same as we did for the case of the bar. We apply the interpolation function in every point. So we have 3 equations for 3 unknowns, A1, A2, A3. Because that's why we selected this polynomial, because we have 3 points. Okay? We can go on. As I said before, we could, for example, there are some authors which have developed more complex elements. For example, you could use not only the joint at the corner, but also at the middle point, okay, at the centroid of the triangle. So you have 4 values. So you can include another term, which is nonlinear, in the interpolation. And you can go on. In this case, the simplest case is 3. So we could define 3 constants, A1, A2, A3. That's all. So we replace them into the expression. And then what we do is we arrange. So we identify in this A1, A2, and 3 multiplied by x and y, which one are multiplied by ui. So, and we collect them and we put it as ni. Same for n2, same for n3. Now, in general, we can define is that we found is that ni, or in general, let's call it that, let's use a different, instead of ni, because that could be wrongly interpreted. This is a general expression. Let's call it let n sub m. The form that they are going to have is this. It's going to be a constant plus a constant times x, and then a constant times y. Okay, so this is for m equal to I, j, and k. And in a minute, I will present these expressions to calculate alpha, beta, and gamma, depending on the positions of the 3 joints. Okay, so with this function of interpolation, we can go on. We can calculate epsilon, because we remember the definitions, du, dx, that's epsilon x, etc. Then with epsilon, we can calculate sigma, because we decided that we will be working with isotropic materials and below the elastic limit. So with U and nu, with E and nu, Young modulus and Poisson ratio, we can calculate stresses from the strains, and then we are ready. We are ready to apply minimum potential energy theorem. So what we have to integrate is the product of sigma x times epsilon x plus sigma y times epsilon y plus tau xy times gamma xy. And we integrate it in the element. And from there, we can identify what we call the stiffness matrix of this element. Okay, to do that, let me go, it's much easier for me to explain that using the transparencies that I posted this morning in the city web. People, did everybody downloaded this file? This is a new version, people. There are some small differences from the previous one. Okay?
Sure.
Yep. Okay, see, this example, remember that we explained it a couple of weeks ago. It's about how to convert a distributed force into equivalent forces in the joints. So that's something that we explained. Now, the new part is here. Okay, so here, CST formulations. CST imply constant strain triangle. Okay, I will explain that in a minute. Okay, so this is our situation. We have the X and Y plane. So we are in the top and we are looking at the plane XY. So we have three joints, I, J, and K. Please, it's extremely important the definition of every element using this order. Okay, there are certain operations that depends on the direction of the definition of the joints. So if in a certain element you define in the other way, you may have problems with this signs. Okay, so please, this direction. Okay, that's positive Z direction. That's the direction in which the number of the joints has to be numbered. Okay, I, J, K. I could be any number, J similarly, and K similarly. But this joints has to be in this order. Please don't forget that. Okay, now, we use the same interpolation for U and V. That's something that I explained. Okay, so the polynomials will be multiplied by values of U or values of V. The values of U and V at the joints can be different, but the interpolation that we use is the same. So what I'm saying is that we could have some values of U and we will have a flat triangle displaced. That's the values of U. And you could have different values for V. You can have a different flat little surface, triangular shape for the V's, okay? Because the values at the joints could be different, but the interpolation, that is obtaining a flat little surface, is the same. Constant plus constant X plus constant Y. That's a linear interpolation. So you obtain a little piece of a flat surface. These are the equations that we apply. Since we're interpolating, we have to recuperate. If we evaluate this function at any joint, we have to recuperate the value at that joint. And those are going to be the unknowns in our problem. Remember? We assume the interpolation so that instead of having to solve the differential equation, we have to solve only for three values: Ui, Uj, Uk. In this case, since this is a 2D problem, we're going to find Ui, Uj, Uk, and also V, Vi, Vj, Vk. Once we find these three values, we interpolate in every element. And we can go on and evaluate strains and stresses and all of that. This is the process that we use in finite elements. After we find A1, A2, and 3, replace, rearrange, and we put it in this way. Now, every one of these functions, n, I, j, k, has this form. I made a mistake here. I forgot this 2a in front of the expression. I'm sorry. So it's 1 over 2a times alpha, beta x, gamma y. We have 3 of these polynomials. Each one of these polynomials is a linear polynomial. So the result of this combination is a linear polynomial. How to evaluate this? This is the way. Please, you don't need to learn by memory all of these formulations, but you need to know where did I get it. Okay, so if I want to evaluate you, I can evaluate in 2 ways. I can ask you to deduce this, one of these expressions. And you have to remember, okay, what I did in order to get this, what I need to do is to remember what's the polynomial of interpolation. That's something that we, you and me, we assume that. We could assume a different interpolation, yes, and the result will be different. But this is the simplest way. Then what? Since it is interpolation, we evaluate that in the joints. Then what? With these 3 equations, we obtain A1, A2, and 3. Then what? We replace them. Then what? We rearrange. And then we identify everything which is multiplied by ui, we call it ni of x and y. Anything which is multiplied by uj, we identify that as nj, which depends on x and y. That's the process. So you could be evaluated like that. But I could also evaluate it in using this in order to calculate, which is the next step. So in that case, I will have to give you these formulations. You have to apply and you go with the calculations to obtain the stress resultants or something like that. Okay? So here you see that alphas, okay, has units of length squared. Beta has units of length. And gamma also has units of length. In this case, A, this large A, is the area of the triangle. Okay, this is twice the area, is this combination. I don't know, see, the first time I started working with this, I said, is this real? Yes, it is. You can check. You can check. You can take any triangle, get the positions of these corners, apply these formulations, and the result is the area, 2a. I'm sorry, twice the area. So if you need the area, you have to divide that by 2, take 2 to the other side. Okay, and you see at least the dimensions are length squared. So now we have completely defined the interpolation polynomials, completely, because if you give me the position of any of these joints, I could calculate the alphas, the betas, the gamma, and the area. With this, I replace into here, and I can define the 3 polynomials. With these 3 polynomials, I can put it into here, and we can develop the interpolation. Okay? Any questions so far, people?
I have a question, doctor.
Mm-hmm. Go on, please.
The value of A1 and A2 are defined, or we must find?
No. The values of A1, A2, and A3, you calculated solving this equation. So this system of equations. So this, see, use UM. Okay, You apply this equation, okay, in each one of these joints. So you say, okay, I'm going to apply this equation at joint xi, yi. Okay. Okay, let me see, what is my pointer here? So at joint I say U evaluated at xi, yi. And the value here has to be U sub I. This is one of my unknowns. Remember, discretization means that instead of trying to instead of trying to find a continuous values of U, I try to find only three: UI, UJ, UK. And inside this element, I assume I take an interpolation. So this is what I'm doing. So this, if I take this interpolation, if I evaluate it in this point, I have to recuperate U sub I. So if I apply this polynomial, I get A1 plus A2 xi plus A3 yi. So this is my first equation. The second equation will be applying this at joint J. So U sub J is equal to A1 plus A2 xj plus A3 yj. And similarly for the third joint, UK is equal to A1 plus A2 xk plus A3 yk. Okay, now, these are the values at the joints. And eventually, those are the values that we are going to calculate. A1, A2, A3, those are the constants of interpolations. We're going to find it. And xi, yi, xj, yj, etc., those values are the position of the three joints that we know, because we already completed the discretization. So we know where those values are. So from here, you have three unknowns, A1, A2, and 3, in three equations. So you find A1, A2, and A3. So these functions, or I'm sorry, these parameters, they depend on UI, I'm sorry, UJ, UK, because you have this in trying to solve this, but also you have XI, YI, etc. So this will appear in each one of these, A1, A2, and 3. And then we proceed to express this in this way. So here, you could identify who is A1, because A1 is the constant. So A1 is going to be what? It's going to be this term here. And if you take alpha I multiplied by UI divided by 2A, that's going to be the first part. Then you also have here a constant term. And here you also have a constant term. So combining all of that, you can identify A1. But you don't really need that. What you really need is to express this in this way. Because this polynomial is going to be multiplied by UI, and that's what you really need to calculate. So the answer to your question, Mr. Wacon, yes, you can, from knowing all of this information, you can evaluate how much is A1, but that's not what you need. What you need to find is what is this polynomial. Wacon?
Yes, doctor. Thanks.
Okay. So let's go on. Now, right now, instead of having a function, continuous function in the domain, we are right now interested in 3 values in one piece of the domain. And this piece, this subdomain is a finite element. And this finite element has a form of a triangle. So let's try to find these 3 values: ui, uj, uk, and also the v's. So in reality, we have 6 unknowns, 3 u's and 3 v's. So we are only trying to find 6 values instead of trying to find the continuous function in this element, accepting that it could be some error. So we can express the first line. You see that this is the first line here. You got an I didn't have a space, but this depends on x and y, similarly for this and similarly for that. Okay, and this is what we had before. This is this. Okay, and you see here that we have presented this in a single vector. So you say that this ui is multiplied by ni, uj is multiplying times nj, and similarly for the uk. But now we recognize that we have 2 functions to interpolate. And we are going to use the same polynomial for interpolation, because this interpolation considers the same 3 points to interpolate both u and v. But considering the position vi, vj, vk, we have to, instead of putting here, we have to put it to the right. Here, here, and here. Okay, and you recognize that in general, for example, you can see that v in the element is going to be equal to vi times ni and xy plus vj nj xy and plus vk times nk of xy, in the same way as we interpolated u. Okay, let's go on. We need strains. Okay, but we just reviewed it in the previous session that epsilon x is equal to what? du with respect to x. Now, u is something like this, right? Here in ni, I have x. Remember, I have 1 over 2a times this thing here is, I'm going to put it in here, and I is equal to 1 over 2a times alpha I plus beta ix plus gamma iy. If I differentiate this with respect to x, I will get 0 here. Here, I will get beta I and 0 here. So, and this will multiply by ui. So I get only this term here, I put it in here, over 2i. And this term here will be multiplied by the first one here, which is ui. Then I have a 0, and then I have similarly for the term which is multiplied times uj. So it's going to survive this one here. And finally, for the k case, this transforms into bk. For the second line, we have epsilon y. Epsilon y is equal to the partial of v with respect to y. So if you differentiate this with respect to y, this term will be 0, this term will be 0, and this is going to be the term which survives. Okay? And as we saw here, this term here is one space to the right. So we have it here, here, and here. And finally, gamma xy, it's du dy plus dv dx. So you differentiate this with respect to y. So this is the only term which survives, but it's multiplied by u. So that's why we put it in here, a gamma. And this provides this term, which is the only one which survives when you differentiate this with respect to x. But it's multiplied v, so that's why we put it into here. So this matrix multiplied by this vector, which is this one here, maybe I should put it into here. This is what we call the vector D, okay? Produces these three elements. And this matrix is what we call the matrix B. And this D vector is the displacement vector. Please, this is the advantage of using finite elements. Instead of trying to find u of xy and v of xy, right now, I'm trying to find only 6 values. 3 for the u's, 3 for the v's, and that's all. In between these 3 joints, we assume the interpolation. That's a linear interpolation. What happens if the exact solution is not linear, it's not a flat little surface? Error. So we have to make as small as we can these elements so that the error is small. That's the idea of the convergence problem. Now, let's go to stress, because we need both in order to apply minimum potential energy. Okay, so we have the 3 elements of the stress tensor that we need to evaluate. And this is Hooke's law multiplied by this. So all of this matrix here is what we call the D matrix. And this vector is this one here. So what we can do is simply multiply D times this vector, which is epsilon there. And this vector epsilon is equal to this matrix B times D. So this is a vector, 3 elements, 3 rows, 1 column, that's a vector. So this D matrix is 3 by 3. This B, you can see here, is 3 by 6. You see you have 6 columns, and the D is a vector, and this vector is 6 by 1. You see that the result is 3 rows and 1 column. That's these 3 elements. Okay, what's next? We have to apply the minimum potential energy to calculate first the U term. Remember, the U term is the strain energy. So this is something that we presented in ship structure class. Okay, so this is epsilon, sigma, epsilon y, gamma, tau. We have here, you see here, I have the epsilons, and here I have the gammas, the sigmas. Okay, so we can say that this is a row. So it's something like this. And this is a vector. So here we have sigma x, sigma y, tau xy. I have epsilon x, epsilon y, and gamma xy. So if we multiply this, we will get this expression, which is an scalar. Now, this is a row, but here I have it as a vector. So what we can do is we can transpose this to replace into here. This is a vector, and we have it here. This is a vector. So we can take this and put it into here. This is what we have done. This Jesus Christ. This is the sigma vector, and this is the rho here. Now, this vector transposed, we have it here. So all what we need to do is transpose this. Remember, when you transpose, you change the order or the position. So the result of this operation is going to be D transpose times B transpose. Okay, and we're going to do that in the next slide here. This is what we have before. So instead of this, we're going to have B times D, and this, we're going to transpose it. So that the result of this is going to be equal to D transpose times B transpose. Okay, so this is a row because D is a vector, and this is a matrix. So this is a 1 by 6, and this is a 6 by 6. 6 by 6. Okay, so the result is going to be 1 by 6, which is a row. This is a row. The other thing is there. Okay, so the differential of the volume is equal to the thickness times the area here. And we assume that the thickness is uniform, so we can take outside the integration. We have D transpose here, B transpose here, dB times D, this is sigma, and the integration on the area. We can go on. Remember, I'm sorry, there's something I forgot to insist here, is the fact that this B matrix is a constant. Doesn't depend on X and Y. It depends on the position of the joints at the corners, but doesn't depend on X as a variable. So this is a constant. That's why we call this, since this is the strain is going to be constant inside the element, that's why we call it CST, constant strain triangle. Inside every triangular element, the strain is going to be constant. Let's put this into here because I think it's pointer options in color. Let's change color. Inside every triangular element, epsilon is constant. Okay, now let's use this into the other integration. So we have this and this. Now here, remember, the B matrix is constant. The D matrix is constant because we are working only with linear elastic materials. Okay? So the integration of this is going to be simply, see, all of this will be outside the integration. In the integration of this dA will give you the area of the element triangle. So we can go on and evaluate that. So the result of this will give you an A, right? This is your A. So we have this D, we put it into here, TA over 2, B over 2, D, B squared, D. Now, each one of these matrices, we can identify completely. I'm sorry, before we go down, this is U. And remember that we have pi, potential energy. It was the combination of this And we said that we were looking for the position where this pi was minimum. So we have to differentiate this with respect to what? Because in general, well, in this case, what we have done is we have assumed the interpolation. And the only parameters that can be changed are the displacement at the joints. So what we can do is simply differentiate with respect to that those unknowns and try to find them such that pi is a minimum. And that's what we do. We differentiate this with respect to D. Now, what we really do is differentiate that with respect to UI, with respect to VI, etc. And then we will get 6 equations. But in a more compact way, we can write it like this, okay? I don't know if there is any mathematician here, but they could be upset, a little bit upset if I write it here. But the sense is this. Here, I have an X, a D transpose, and here I have a D. So if I multiply this times that, it's like having an X squared. If I differentiate that with respect to X, I will get 2 times D to the first power. And this is what I'm writing here. The 2 that I get here cancels with this one here, and I get only 1 D here when I put it under here. So as a result, all of this up to here is going to be the stiffness matrix of one triangular constant strain triangle element. Okay? And to complete this part, remember in B, I have 1 over 2a in the denominator. Let me go back so you remember that. Here, I have 1 over 2a. So I have 1 over 2a here and 1 over 2a here. So I would have 1 over 4a squared. But I have 1a here, so I got 4a in the denominator. The t is here. The e over 1 minus nu squared comes from the d, and this is the result. So what we have to do is we have to do this operation in order to get a 6 by 6 stiffness matrix for every element. Questions, people? Questions? In the case of the beams, remember, we have local and then global reference system. In this case, since we are in the flat surface, both systems for reference system coincide. So you can think that X is always to the right and Y is always in that direction for the global and for the local. So there is no need to transform anything like that. If we could try to put 2 surfaces in the space, then we will need to do this transformation. That's what it is done inside the computer program. We don't have the time to go over that. But at least you saw that in chapter 1 and 2. You saw what we have to do. We have to go from local to global, form the global matrix, solve for the global displacement, and then for each element, you go back. You go from global to local for every element and solve it. In this case, since the local and the global coincide, we don't have to do this when we save some time. Okay, let's take a break here. And when we return, we are going to explain how to do this, to implement this into a simple example.